It's biology with Mr. V. Biology with Mr. V. That's me! Hello, Year 12. So I'm making this little video to try my best to go through details of fish and insect ventilation in a way that's hopefully better than just looking at a textbook. So I'm just going to work through the PowerPoint that I sent you. But where I can, I'm going to stop. I'm going to go over with a bit more review. I'm going to use Mrs. Bateson's really cool, remarkable tablet so you can see me writing and doing things as we go. So let's just see what happens, and hopefully this will be all right. So, firstly, fish stuff. Now, one of the groups has not done the dissection. I'm sorry for that. It's just one of those things. I'll make sure we do it when you come back. All the fish are in the freezer. Presuming there's no sort of issues with that, then it should be ready for when we come back, whenever that may be. Key idea though with fishies, water needs to go over the gills. If water needs to go over the gills, well, it needs to do so in such a way where there is an input and an output, so it flows over the gills in only one direction. The way the fish do that is they open their mouths. So when you see a fish going nom 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 nom, they're not gulping, they're not randomly drinking water. They are literally trying to take in as much water as they can to get that water flowing over the gills, and then out of the gill plates and out of the fish itself. The few extra little keywords that come in here are when we actually open our mouth, the inside of the fish's mouth here we call the buccal or buccal cavity. And therefore, the fish can actually both lower and raise the floor of their mouth, the floor of this buccal cavity, which changes the volume of it. And if we're changing volume, we're therefore changing pressure. So what you'll find is they'll get the buccal cavity as wide as they can, as open as they can. By increasing the volume lots and lots, they decrease the pressure, so water floods in to the buccal cavity. The next route is that water will actually go over the gills and into a second cavity called the opercular cavity. The opercular cavity is only surrounded by a little bony plate called an operculum. If ever you watch fish, you actually watch their sort of the sides where you'd think their gills are. You watch the little side flaps opening and closing. That's actually the operculum, a bony cavity that opens to let the water out and closes to keep the water in. So the water will flow into the buccal cavity, over the gills, into the opercular cavity, and then out to the fish when the operculum, the bony little plate, opens itself. If we zoom in on the gills, we've got a few extra little bits that we can label. Most fish have sort of like 4 or 5 little gill arches, and coming off the gill arches, we have gill filaments. Now, obviously, these gill filaments, think of them like you would like the hairs on a root. They're going to give it a massive surface area. Now, I am on the belief that I reckon it'll be far easier, rather than calling these gill filaments, these little strands, call them primary lamellae. Because that'll then explain what a secondary lamellae is. Now, you can't see this on this diagram, but the diagram, one of the ones in the textbook, does have it. On each of these primary lamellae, there are little extra folds. Those extra folds are called the secondary lamellae. And it's the secondary lamellae where all the gas exchange will actually take place. Now, the only extra thing here is, as the water is flowing over this primary and secondary lamellae, the blood is flowing in the capillaries in the opposite direction. So the blood is flowing in opposite direction from the heart, so this end is the arterial end, over the capillaries to the venous end. We call this idea countercurrent. The water is flowing in an opposite direction to the blood. It's countercurrent. If they were flowing in the same direction, that would be concurrent or parallel. So I asked the question for you to think about, why is a countercurrent flow more efficient for gas exchange in fish compared to concurrent? And the next slide, tried my best to go through that. So the blood flowing in opposite directions. The only thing that matters, the only reason you have a countercurrent system is to create a gradient create a concentration gradient of oxygen that is maintained the entire way across the gills. So if you imagine, let's see if I can get this to work. Sorry, bear with. I can't remember Mrs. Bateson's birthday, so I can't unlock this remarkable tablet. Yeah, I got it right. I do know when she's born. So, if you imagine the water is flowing this way. So the water is flowing here. It will be in the buccal cavity. And here is where it flows into the opercular cavity before it eventually goes outside. Well, goes outside the fish and back into the sea or the river or the lake. If we think about it from an oxygen point of view, in the buccal cavity, there's been absolutely no oxygen diffusion. So we could say that the percentage of oxygen available is as much as they ever could be that's dissolved in the water, is 100%. If the blood's flowing this way, well, in terms of oxygen concentration, it shouldn't have any. If it's not been to the gills yet, well, where it starts should be 0%. It shouldn't have any oxygen. Now, straight away, you've got a really steep concentration gradient there, but they're not together. The 100% isn't next to the 0%. You're not going to get diffusion between them. But of course, being 100% sort of oxygen here, I say 100% really, really lightly, guys. You appreciate the water is not 100% oxygen. There are clearly lots of other particles, elements, bits within. It's just 100% of the maximum available oxygen there would have been anyway. That concentration there where there is at the start by the buccal cavity is always going to be more oxygen in the water than there is the blood flow. Always. So as that oxygen is diffusing, well, the amount of oxygen in that water becomes less and less and less as you go along it. But because this side had 0%, even though there's now only 20% of oxygen right by the opercular cavity end, well, that is still a concentration gradient, which means diffusion can still take place. So obviously, as more and more oxygen gets into this system, this will increase, that's supposed to be 60. More and more oxygen gets into the blood flow. Well, at every single point, there is a concentration gradient. It's not necessarily a really, really steep concentration gradient, but it is a concentration gradient. So along that gill filament, along the lamellae, virtually all the oxygen that was in the water will be able to diffuse into the blood and into the fish. If it was a concurrent flow, I'm going to go back to the PowerPoint for this bit. If it was concurrent, yeah, you'd get an amazingly steep gradient at the beginning, so loads of diffusion of oxygen into the blood at the start, but halfway across you'll get an equilibrium, and then there'll be no net movement, which means in this case 60% of that oxygen that was in that water doesn't diffuse across. But in a countercurrent flow, all right, not a steep gradient, but you get constant diffusion down the entire length, which means overall more oxygen diffuses into the fish's blood, which makes it more efficient. Okie doke. Next little job is I set you a reordering task. So these were the steps involved in actually how the fish actually ventilates itself. How does that water actually move down the pressure gradients in the fish? I put the answer, hopefully I did mix that up. It looks mixed up. Let's see. Hopefully I did mix it up, and your answer should have been, the mouth opens. Lower the buccal cavity floor. What you're doing there is increasing the volume inside the buccal cavity, and therefore decreasing pressure of it compared to the outside world. Water will rush into the mouth down a pressure gradient. The opercular cavity expands. Think of it, that's increasing its volume. You raise the buccal cavity floor, which lowers the volume of the buccal cavity. So the pressure inside the bronchial cavity is now higher than the opercular, so water moves over the gills into the opercular cavity. The mouth's now closed, operculum opens, and the sides of that opercular cavity move inwards, increasing the pressure inside it, and water rushes out the fish through the operculum, through that little bony plate. Boom. Great. Insects. I hope you did have a go at actually trying to draw it just based on the instructions. It's a really fun game to play, trying to draw any sort of biological component. As long as you know its rules, you know sort of things it must have, can you get it right? And I hope you were actually relatively straight. I hope you were relatively close if you did give this a go. What we're looking for is, we're looking for a system of lots and lots of pores all along the thorax and the abdomen of that insect. And these pores are called spiracles. A spiracle, think of it like, in mammals, we have a mouth. In insects, they have lots and lots of spiracles around their exoskeleton, which is like the tough layer that protects their outside, because obviously they don't have bones like we do. Air is able to get into the spiracle and into all of these tubes here. The main tube is called the trachea. So just like we have a trachea, they have a trachea too. Big difference, their trachea does not have rings of cartilage, but they still need something to prevent their trachea from collapsing under low pressure. So they have a structural protein called chitin. I'm going to set you a few questions later today, and one is a brilliant question of chitin as a structural molecule, comparing it to the structural carbohydrate of cellulose. Generally, absolutely cracking question. Chitin. Tracheas branch off not into bronchi, not into bronchioles, that's only mammals. These guys branch off into tracheoles, and the tracheoles have an open end. And this open end literally bathes straight into the tissue fluid that surrounds all the tissues, all the cells of that insect. Insects don't have a normal, I say normal, that's a bit harsh on them. Insects do not have a mammalian circulatory system. They don't have blood vessels. They've got a heart, but that's it. So without blood vessels, we say that system, by the way, is an open system, whereas ours with blood vessels is a closed system. So rather than the oxygen going straight into the blood, well, actually it goes into the tracheal, it goes into the tracheal fluid, which then bathes into the tissue fluid. So oxygen is effectively delivered directly to the tissues, more or less. One of the things we have to consider when we talk about why do organisms have, I'm sorry that I've just scribbled very active out instead of underlining it. One of the things we have to talk about was why do we need a ventilation system? Why did organisms need a gas exchange system? Size, surface area to volume ratio, but also level of activity. Insects are very, very active organisms. Now they are what we'd call, they are exotherms, cold-blooded, but they are still very, very active, mainly because they fly. So they do need a very good supply of oxygen for aerobic respiration. You can't get away with saying insects have a low metabolic rate. They don't. They've got a really high one. One way that they maximize the oxygen uptake to ensure they can do enough aerobic respiration for things like flight is what they can do is they can withdraw the fluid inside the tracheals and the tracheoles. So this fluid can go all the way up really. But if they withdraw it, it actually means there's more surface area between the tracheole and the cells around it. So yeah, oxygen will obviously diffuse into the tracheal fluid, but it also can diffuse into the cells nearby. So the more space, the more fluid, the more diffusion into those active tissues. Larger insects have a few extra little specialities on how they can ventilate themselves. But the idea is always going to be the same. That's Mrs. Bateson grabbing a dinosaur costume.
Yeah.
She's going to have lots of fun with Cassie. Either way, any idea of ventilation has to be because you change the volume of a part of the body, which changes the pressure. And then air will always move down a pressure gradient. There were 3 ways that the textbook details how larger insects can try and do this. The first one was something that locusts can do. So I'm just going to, because it's such a quick video, I'm just going to play it. Discard. It looks like they're breathing. It literally looks like they're breathing. Can you also see here? That is a spiracle, and you can see it opening and closing in time with the change in volume that they're creating in their abdomen. Oh, pause. So let's go back here. So they're changing the volume of their abdomen. It literally looks like we breathe with our ribs moving up and down, doesn't it? So think, when the abdomen expands, that's like when we breathe in and the rib cage expands. What they're doing is they're increasing the volume as the abdomen expands, or they're increasing the volume of the abdomen. They purposely open their spiracles in the front part of their body, and because you've increased the volume, you've also decreased the pressure. So air will move into the spiracles from a higher pressure outside the insects to the lower pressure into the abdomen. Great. Air into the tracheal system. Those larger insects now have oxygen. Opposite, if they reduce the abdomen's volume, so it looks like they're breathing out, again, what they've done there is decrease the pressure, decrease the volume, so increase the pressure inside the abdomen. The pressure inside the abdomen will now be larger than the external environmental pressure, open some spiracles at the rear of their body, and air leaves. So it more or less replicates what humans do with changing the diaphragm and changing the rib cage and that shape. More or less replicates it. And by opening and closing the spiracles in the front and rear of the body at the right time, they're ensuring a flow of air constantly through. So for larger insects, who of course have a slightly smaller surface area to volume ratio, and therefore need to ensure the system's a little bit more efficient, that's how they can do it. There's a couple of the little things that can be done. There are, in quite a lot of insects, part of that tracheal system are expanded and are flexible walls. So rather than just going, if I go back to this bit, rather than just going into sort of like a flat surface, it actually looks like it looks like an alveoli. Or something far ruder. I'll get rid of that. It looks like an alveoli. And if the flight muscles are squeezing those little air sacs, well, that's going to push air in and out. So that's going to help ventilate the system, bring new air in, and air that's already had the oxygen diffused out, that's going to get rid of it. Some insects can move their wings, and that can alter the volume of the thorax, apparently. And again, if we're changing the volume of the thorax, we're changing the pressure. If the pressure changes, air can move in or out of the tracheal system along that pressure gradient. There you go. That's what I've got in terms of me going through and just trying to talk the science at you. Obviously, you've got this video now to sort of stop, replay, go back. You're welcome to find far better videos. I couldn't really find that many decent ones to do with OCR spec on insects, but there are quite a few to do with fish out there. Either way, pop me a question via email if you get any. The task at the very back of the booklet has a little question about fish and a little question about insects. And I'd just like to just very quickly go through this before I set you off with a little bit more work via email. So the first one, bony fish and insects have different gas exchange systems. Both can be observed by dissection. How would you carry out the dissection to display maximum detail of either gas exchange system? So obviously, I significantly hope that you went to try and talk about the fish system, because that's the one that 2 of the groups have done. The third group, I appreciate if you've only seen a video. So what we're looking for is, with fish, you would remove the operculum, or at least move it out of the way. And then you display the gills, so maybe by placing them underwater. If you were to do it with insects, all you'd do is you'd cut open the exoskeleton, the outside part, and then you display the tracheoles, usually by staining them. For the second question, it gives you a lot of information about beetles, where they live, and some details for how they carry out investigation into the effect of temperature on 3 diving beetles. Notice that they haven't used anything higher than 30 degrees. Thank God. Otherwise you'd have boiled beetle. Something is apparently wrong in that table, and you just had to write the correct answer next to it. Doesn't seem anything wrong with the headings. Doesn't seem anything really wrong with the data, which means if there's an error, it must be in a calculation. 10 plus 12 plus 8 divided by 3 is 10. 44 plus 48 plus 38, yeah, that is 43. If you add 18, 22 and 18 together and divide by 3, you do not get 19. Sorry, you do not get 20. Instead, you do get 19. So that's what I'm looking for. Some sort of indication that 20 is incorrect by circling it or crossing it or whatever. And then you've written the number 19 either in the table or in the space below, either way. Last question. The structure labelled A, so the spiracle, it goes into trachea, and then the trachea branches off into what these A's are, so they are the tracheoles. And describe how that trachea of a mammal is different from a trachea shown of the insect gas exchange system for 2 marks. So reality, guys, I'm just looking for as many comparisons as you could give, because it's only 2 marks. I'm sure you can appreciate 2 comparisons is all you need. So any 2 of these, but it has to be comparative. If you say it anywhere, then we presume it's the mammal, not the insect, because the mammal goes first in the question. How is the mammal different from this diagram? So mammals only have 1 trachea, but obviously insects have multiple because they have multiple spiracles. Mammals have a much larger diameter, insects much smaller diameter. You can say wider trachea or narrower in the case of the insects. Bigger was not accepted. Bigger trachea, nah, it's all about being wider. In mammals, trachea's got cartilage, but in insects they have chitin. Mammals have C-shaped rings of that cartilage, but insects, theirs is actually spiral. It looks like it could be C-shaped, but I promise you it's all the way around for chitin. It's spiral. The mammalian trachea is much longer, the insects is much shorter. Mammalian trachea branch into bronchi, but these guys' tracheas branch into tracheoles. And mammal trachea has smooth muscle, goblet cells, ciliate epithelium, all those tissues which we learnt about, but insect trachea have none of them. No mucus if you're an insect. Okie doke. That's my PowerPoint. That's my video. Check your emails because I'm going to be setting some work alongside this. So thanks very much for listening. Peace out, ladies and gentlemen.